Welcome to our Solutions for NanoAnalysis podcast, brought to you by Bruker NanoAnalysis. We look forward to bringing you a new podcast regularly. My name is Cody Morton. I'm a marketing communications specialist at Bruker NanoAnalysis and an information enthusiast. If you like to learn from specialists in their field and hear what technologies are solving their problems, you will enjoy this podcast. Every session, we will focus on a different problem that our colleagues face in the lab and in the field. Some of the solutions will be a variation of ideas you may have heard before or even worked with. We will bring you these topics in a new and interesting way and introduce you to updated and thought-provoking results. We will talk about how the problem was dealt with in the past and what we're doing to solve the problem now and perhaps even envision future solutions. Join us as we talk solutions with a variety of scientists and technicians in many different industries in the Solutions for NanoAnalysis podcast. Today, we are talking about the advancements being made by simplicity delivering affordable science. We are happy to discuss the addition of our EBSD detectors to benchtop SEMs with some terrific results. Join us while we talk about how labs with limited resources can get outstanding results. To talk about this new technology, welcome our EBSD product manager, Daniel Goran. Daniel acquired his PhD at Metz University in France, and in 2009, he joined Bruker NanoAnalysis as an application scientist. Since 2012, Daniel has been our EBSD product manager. Also joining us is Mike Toalson, a distributor for Coxem, a manufacturer of benchtop SEM systems. Let's talk about the ED-XS for smaller benchtop systems. Mike, thank you so much for joining us today. Would you mind telling everybody who you are in the world?
Thanks, Cody, for the invitation. My name's Mike. I am the general manager for Element Pi. We are the USA distributor for Coxem scanning electron microscopes out of South Korea. And we've been doing this since 2018.
Terrific. And Coxem, for those that maybe have little background with them, tell us more about that company and what they offer to their customers.
Yeah, Coxem is one of three companies that got started in 2007 in South Korea as a result of a technology licensing effort by the Korean Research Institute for Science and Standards, which is CRIS. It's similar to the NIST here in the US. So they started brand new company, and they focus 100% on electron microscopes. And because of the way they were started, their primary focus was cells in Southeast Asia. And it wasn't until 2017 that they decided to venture outside to other parts of the world, and we got connected and brought them to the U.S.
So I noticed, Mike, when I look at the Coxem images of the system itself compared to other SEMs I see in lab settings, it looks a lot smaller. Is that the case? Is it a smaller system?
Well, it's certainly smaller than floor model systems that take up an entire room a lot of times because of all the power supplies and the other utilities that they require. But from a tabletop standpoint, I think most of the tabletops on the market they're all roughly about the same size, typically about 16-inch by 24-inch footprint, or which would be 400 millimeters by 600 millimeters for those that prefer metric, like me. Yeah, so they fit on standard desktops, everything. So,
who are the customers that most benefit from this size of system?
Well, we have customers in just about every facet of research you can imagine, from obviously academic is a big area, but also in government and in industry. And over the last 3 years, I'd say the primary focus has been all related to energy. There's just so much research going on with battery materials and everything associated with that. But we've had people in aerospace, food science, packaging materials, biology. I mean, just about you run the gamut of technical areas, and we've probably got a customer We even have a customer that does equipment for root canals in dentistry, and they use our equipment for looking at the teeth, cadaver teeth, I guess, and they look at them for how the equipment works, and they make use of they like our mosaic or panorama feature because they need to do low magnification images that they can zoom into, and so we have a feature where you can actually create a large area image at high resolution. We call it panorama, and they like that and make use of it really well.
Oh, that's really interesting. The Coxem is something that quality labs get a lot of use out of as well?
Yeah, exactly. So, the big thing about these tabletop systems is that they serve more of a general purpose, and quality control being one of those. So, what's nice is that the multi-user instrument, because of its robustness, and multiple users can bring samples. Engineer has a problem out of the factory or whatever, they can bring a part in and look at it real quick to figure out what's going on. They don't have to wait. They can get immediate results. But yeah, we've got customers that are using it 24/7 for things in semiconductors, and a variety of different things where, it's in a quality control lab and they're doing a measurement or something that requires an electron microscope, but it doesn't necessarily require a big microscope. So, they probably got a big microscope in another research lab, and then they can use the tabletop system to do, the basic kind of imaging on a repeatable basis. So,
Daniel, what is the problem that we're solving today?
So to answer your question, I would like to say a few words about a product vision as to why we did this. And the reason why we developed this product and we launched this product is because we believe we can contribute to the scientific and technological advancement. And how we want to achieve that? It's by significantly decreasing the cost of EDS and EBSD. Entry-level electron microscopes, either if they are tabletops or compact or standard tungsten SEMs, do not have EBSD, is because the EBSD technique has been until now very expensive. And that would, in certain cases, if you add EDS and EBSD, would triple the cost of the microscope or maybe more. And then, of course, makes it not very probable that a customer with a limited budget would afford to add EDS and EBSD on their entry-level microscope. It's not that much of a question of size of the detector or weight of the detector. It's important, that technical point. But it is mainly because of the economics. It's really an economical question. It is true that, let's say, if the cost or the commercial part of this new product, it is very important. It represents maybe 80% of the entire picture. The size of the detector or the weight of the detector, it's also important because usually EBSD detectors are very bulky and heavy. And if you install such a detector on a tabletop microscope, you will run into problems, let's say, because it will really maybe not tilt the detector off the table, but the microscope off the table, but it may not fit onto the microscope. And with that in mind, we had to design a new EBSD detector with a different functioning principle because we had to make it really small and simple to use and lightweight. So the detector is powered by a binning capable CMOS camera with a native resolution of 720 by 540 pixels. It can do any binning from 2x2 up to 6x6. And no matter the binning mode, it can reach a maximum speed of 520 frames per second. We were talking earlier about the dimensions and the weight of it. And here you have a picture just to have a reference as to how small it is. It's next to a Bruker ball pen. So it's 3.3 approximately inches long and less than 2 inches in diameter. and it weighs less than a kilo. And also extremely important, it is a true plug-and-play device. The power transfer and data transfer is done through a USB 3 cable. So it connects plug and play into a computer. You only need a USB 3 port on the computer side. Like all Bruker EBSD detectors, it has a user replaceable phospho screen, and it has a user removable detector head with a special slide in, slide out mechanism. So you can take that, remove it from the rest of the detector and free up the chamber, the SEM chamber. And last but not least, it has a special custom-made optic system with a field lens to maximize light throughput.
So, Daniel, when you're looking at this size versus the full-size EBSD that Bruker offers, it's less than half the size, isn't it?
It's way more than that.
I was just saying.
Is at least one order of magnitude, so at least 10 times smaller. I don't have a picture to really show the XS next to a standard EBSD detector, but I do have a picture. People maybe have seen the EM30, the tabletop SEM from Coxem, and you can see the EBSD detector. It's really, really tiny.
Yeah. Now, the small detector, the XS, is that something that's only available on the smaller scopes?
Yeah, that's a very good question. This special functioning principle, which I mentioned earlier, which we had to implement in this new detector, it means it does not have a insertion retraction mechanism. And for that reason, we're related to the physics of optics and focal distances. And so this detector is optimized for SEMs with small chambers and medium-sized chambers. The tabletop being one of them.
Okay. So how does the software then compare with the XS versus, what are we calling it, the full size or the original?
Yeah. That's a very important point. Typically, when EDS is installed on these entry-level microscopes, it comes with a basic or a compact version of a software with very limited capabilities. We decided that should not be the case for this product, for Quantax ED-XS. And Quantax ED-XS comes with the EBSD detector that we just spoke about, with a 30 square millimeter EDS detector, liquid nitrogen free SDD, with 129 EV manganese K alpha resolution. It has an element range from boron to americium, and a fixed design, meaning the detector cannot be inserted or retracted. It's in the measurement position all the time. And in terms of software, it comes with the standard EDS capabilities and the full capabilities for EBSD. And this is our ESPRIT2 main product software.
So this is really opening up the options for a lot of labs that aren't able to get maybe funding for a much bigger system, universities, education labs, startup labs. Where do you see this technology going from here? Is it just going to keep getting smaller and smaller so that it's eventually a button you just put in there?
Well, we're not yet there. And certainly that will require effort, not that much on the hardware side, but on the software side, to make the software more intelligent, take over some decision making, for example, in the setting of the hardware before a measurement, or deciding what kind of step size to use and so on. But we're not yet there. There are we are half the way there, let's say, but hopefully soon we will see development or of features released in that direction. Mm-hmm. But where we see this going, this product is, the idea behind this product is to make the lab's resources to be used in the most efficient way possible. And here I have 4 very important points or major benefits of this new product. So the major advantage of the new EBSD detector is that it will help lab managers to use their resources as efficiently as possible. And when I say this, I mean for all applications, all EBSD applications not requiring the spatial resolution of field emission SEM. So for materials having grain sizes or particle sizes, let's say larger than a half a micron, that would be a routine analysis, and all those measurements could be done with an entry-level SEM, with a tabletop SEM, using this new system of ours. Then training new users could now be done at much lower cost and time constraints. And this is particularly important for academia, where they get master students, PhD students every year, and they need to train them. And if you have just one EBSD capable microscope in the lab, and it costed $500,000 or $1 million to install, the constraints would be really, really large there. Then having such a affordable system in the lab would give the lab managers could give more time to entry-level users to practice EDS and EBSD. So again, for academia, it's very, very important not just to give these new users a session of training, but afterwards for them to take their time to practice and get good with EBSD and EDS. And if their applications require a powerful, high-resolution SEM, they could go and do their measurements there, but only after they have become very proficient with the techniques. And then last but not least, for those who have done EBSD already, they would know that sample preparation, it's quite, let's say, demanding for EBSD, and therefore you may not get it right from the first shot. So such a system in the lab could be a very good way of checking the sample preparation quality before a user goes and keeps an expensive SEM busy without risking to realize that the sample was not prepared well enough and then ruin that time on the expensive SEM.
I think probably with the entry-level users, the sample prep is one of those skills that's very important to perfect early.
Yes. Yeah, absolutely. And then this is a very efficient way or affordable way to give them time to have this iteration done. Preparation, go check in the SEM. It's not good enough. Go back to the preparation, do some more final polishing, go back to the SEM, and you cannot do in a busy lab that with an expensive field emission SEM because the schedule is sometimes booked at least 2 weeks in advance. While if you have like a tabletop SEM retrofitted with EDS and EBSD, you have a lot less constraints, time constraints, and users could do that and use that SEM, that facility for checking the sample preparation quality.
So Daniel is telling us all about adding EBSD to the system. How do you think that adding the EBSD ED-XS to the Coxem system will help the Coxem customer?
Yeah, so first, I guess, I think the reason Daniel and Bruker got together with us is because we're kind of in a unique position with our tabletop system. Our tabletop system's chamber is the only one on the market that has multiple chamber ports where you can access inside the chamber. Normally, with a tabletop system, they have one chamber port, and that's used for the EDS detector. And so on the Coxem system, we actually have 3 ports: one in the front, one on the left, the back, the right, and the back. And of course, you've got the front is where the door is, the chamber door, and which it's actually got. I guess you could call it a 4th because there's electrical feed through the front door. But anyway, because we have that extra port on the side, we were able to figure out a way to mount the EBSD. So as far as the customers that would benefit from this, I think it'll primarily be in the people that have asked about it in the past have been in mineralogy and metallurgy, looking at grain structures and identification of minerals because of their crystalline pattern. But we've also had people that are doing basic materials, fundamental materials research, in crystals, crystallography. I mean, all kinds of new energy materials that are also interested in those kind of things. So, and they don't necessarily need a high-end system to do that. But especially in geology and metallurgy at the academic level, I think it'll be a really, really great teaching tool for students to learn how to use EBSD for those kind of analysis. And then it'll be a good stepping stone for people before they move up to a big, expensive system that a lab manager might not be crazy about allowing a new person on their $1 million or $500,000 system. They might be a lot more prone to letting them, get their feet wet on a lower cost system first, and learning all the basics so that they're not utilizing a lot of expensive microscope time.
Now, if someone already has a smaller system like a Coxem system, is this something that they can add on, or do they have to start from scratch again with their system?
The answer is yes, providing that port is this port here is available. This port was not designed for what we are using it for. So that port was designed for a STEM aperture. In case the microscope does not have that STEM aperture or that STEM detector solution, then the port will be free and they can use it as is. Otherwise, they will have to take down that detector and install the EDS in EBSD.
How will this technology change the way that labs work with their samples? Does this expand the type of sample they can run or allow a more intense look at their current samples?
Well, part of the product is EDS, so they might even have already EDS on the microscope. It is the EDS detector that is currently being sold with this microscope goes on a port which is opposite on the chamber. So it's facing these 2 new detectors. So there will be nothing different compared to that in terms of EDS. If they didn't have EDS, then they could do EDS now. And then in regards to EBSD, the 2 techniques, they are quite different. They are very different. They provide very different information. But in many cases, it's a very powerful complementary information, because there are certain types of analysis EDS alone cannot do, and certain types of analysis EBSD cannot do. And when you have an integrated system, there are certain synergies for specific applications where the 2 techniques can help each other. For example, I can give a few examples. You have titanium oxides, the 2 famous polymorphs, the rutile and anatase, which chemically are identical, but crystallographically they are very different. So then EBSD would be able to separate absolutely no problem those 2 phases. And then there are many metals which have the same structure, which for EBSD will look identical or will look very much the same, like copper, nickel, gold, silver, you name it, aluminum. And then for EDS, they will be extremely different. So then you could use the EDS information to separate in an EBSD map these phases, creating very, very similar pattern, Kikuchi patterns. So to go back to your question, adding EBSD would most of the benefit would be additional information, and to only part of very few, some of the applications the customers have already looked at either with just microscopy or EDS. EBSD would simply add some extra information to that, but otherwise there will be types of analyses which are not possible otherwise with either just electron microscopy or EDS alone. For example, that would be grain size and shape statistics, which are more or less fully automated with EBSD and with this system.
Daniel, do you have an example you can share with us using this EBSD technique?
I have here an example of a map acquired from commercially available aluminum foil. So there was absolutely no sample preparation done. It's just the aluminum foil from the shop, from any shop on this planet. You can find aluminum foil. And then, so we acquired an EBSD map. You can see here what we call the pattern quality map. And you can see these parallel dark lines. These are practically defects on the foil produced by the rolling process, which is how the foil is obtained from aluminum slabs. And here is the orientation map, where we can see that the grains, the crystals in the aluminum foil have a preferred orientation. The fact that they are mostly blue or purple and not just all the colors, that means the aluminum foil we can find in the shops have a preferred, microstructures with grains with a preferred orientation. And if we use this data and ask the software to reconstruct the grains, then we can obtain, it's fully automated, the process, a map, and it takes a few seconds, a map that looks like this, where all the grains have been detected and they are colored with a random color so that there are no two neighbors with the same color, simply to make them visible to the human eye. And if we look at then statistics, here we have the grain size distribution, where we have a nice peak to the left, let's say for grains smaller than 4 microns, and then some of these classes of larger grains, and one of them here almost 13 microns in size. And there were 892 grains in this map, and they have an average grain diameter of 5.15 microns. And also, in the same time, you can also, the software calculates the shape, the form of the grains. And you can have here a distribution of the grain shape with 0 here, meaning infinitely flat, and 1 meaning a perfect circle. So the grain looks like a circle, like a perfect circle. And you can see that there is a peak centered around 6.5 to 7, or 0.65 or 0.7, which means some of the grains are a little bit flattened, but most of them are relatively equiax. So all these, whatever I show you here, this is fully automated process. The user only has to click one button.
Daniel, finally, as we're talking about this technology, who would benefit most, in your opinion, with this size system and this new technology being offered?
Thank you for that. It's a very, very important question, and I hope I can make it crystal clear. The new product is intended for newcomers as well. That's clear. For the part of the microscopy, electron microscopy market, which has not been served with EBSD until now, but it's not exclusive to that part of the market. It is also intended for the existing EBSD users, for those users which, for big labs, for academia labs, for private industry, where they are already using EBSD, so they are only looking into making their work more productive or use their money better, let's say.
Mike, one last thought for you. It sounds like when you're working with the microscopes, time is money, and larger system has a lot more time requirements. Does this play into the cost of ownership for your customers?
Yeah, exactly. I mean, that's when you look at the cost of ownership, obviously big microscopes have a, much higher cost of ownership. So it's not only that, but then, at universities where they have a central core lab, the departments have to rent time they have to reserve time first, but get it on the schedule. Then they have to, go to the lab, which is always on the other side of campus and never fails. And they're having to pay for that in some fashion. So we've seen a lot of the academic departments decide, hey, let's put a tabletop in our department that we can use to cover 75% of the work that we need to do all of our upfront work here, and then when we're ready to do the final really the high end analysis or imaging, we'll go over and get on the big system. So I think it's just been a gamut of different reasons for people to investigate that.
Thank you to our speakers today. As an added bonus, Daniel has put together a comparison sheet for people that might be looking at adding a benchtop system to their lab. Stay tuned at the end of our podcast for more on this topic. If you would like more information about today's topic or to submit a topic idea, please email info.bna@bruker.com. You can also check out more information in today's show notes. A complete deck of information is available now in the notes for you to download on today's topic, including some results images and technical information. Join us next time as we look at a new solution with more scientists and technicians in all sorts of industries. I believe you have some extra information prepared for those people that might be really serious about comparing costs, Daniel.
If I can call it that way. And I prepared 2 slides where I would like to clarify that value for the money, or that value proposition we are making to these existing users. Here you can see a table where we have different factors to consider, and we compare the numbers of the ED-XS, Quantax ED-XS on EM30, the Coxem tabletop, and most of the numbers refer to the EBSD detectors. And then compare with a conventional EDS and EBSD system, which usually goes on a field emission SEM. So if you compare the maximum speed, for example, for EBSD, that would be 520 for eFlash-XS, and up to 4,500 frames per second for a latest generation CMOS fast EBSD detector. Then if you consider doing EDS and EBSD simultaneously, then the EDS technique will slow down dramatically the speed at which you can map, because you may want to have a good number of counts in every spectrum acquired in every point of the map. So then the maximum speeds would be around 100 points per second for the ED-XS, and around 350 points per second for a conventional EDS-EBSD system. Now, if we talk about EBSD, most maps have like 250,000, 300,000 pixels in them. But here I considered a very, let's say, general situation where a user would want to acquire on a batch of 20 samples, for example, 1 map per sample, 500,000 points map. And how much time would that take? Would take approximately 16 minutes with eFlash-XS and 2 minutes with a very fast EBSD detector. So if you compare these two, you see that you will be a lot more productive with a conventional EBSD detector. But now, if you consider then an 8-hour work window per day, how many samples one could analyze in one day? And the difference is not 8 times more samples, because you need to vent the microscope, exchange the sample, pump the chamber, and prepare the system to launch the next map. And that for an, let's say, reasonably experienced technician would take, let's say, 10 minutes, maybe more, but let's say 10 minutes. And then that means with ED-XS, a technician could acquire 18 maps or 18 samples, analyze 18 samples in 8 hours, and 40 samples with a conventional EBSD system. But now, if we consider the cost of each of these systems, so if you normalize by the cost factor, then ED-XS is at least 4 times, so it's a quarter of the initial investment. And then if you normalize by that, then you actually, per dollar invested, you are more productive than when you have a conventional CMOS EBSD detector. And you almost twice the productivity. So practically the takeaway messages are for low budgets or organizations which may not be willing to take high risk investment risks, then they could buy the EM30 with ED-XS, and that would provide them an integrated EDS EBSD capability at 1/4 the cost of a conventional solution. For those which are well funded, for the same money, they could get 4 EM30 tabletops with ED-XS, and that would give them twice the productivity. And in case one system fails, they will still be at 75% of capacity. While if you have a conventional system and in the FCM it's offline or the EBSD detector it's offline, then you're at 0 capacity. You're on downtime. If this is not convincing enough, then I have a second slide where this time I consider not the initial investment, but the cost of ownership and downtime, because those are very often not considered in the discussion. And I would like to emphasize it here. The eFlash-XS was designed with reducing as much as possible the cost of ownership and the downtime. So due to detector complexity, the detector complexity is very low. Reliability, it's very, very high for the eFlash-XS. And the downtime, will be very, very low because we will have field replacement units. Practically, we will ship locally a replacement unit within days, which the user can then swap with the failed unit by themselves. And also, what happens when the EBSD screen gets damaged, which can happen? Well, the user can immediately replace it with a spare screen when it comes to our system, to the XS system, while if you have a CMOS conventional EBSD detector, you have to ship the detector back to the factory for a very expensive repair, and that's because the screen is fiber coupled with the CMOS chip in the camera. So when you consider these important factors, and also a spare screen, it's $1,500. I don't know how much it will cost to ship to the factory and to have the screen replaced, basically. And also add to that the downtime. This would be a very, very much higher cost of ownership compared to the eFlash-XS solution.